Hey everyone, welcome back. Look, if you are gearing up for your chemistry exam and you just want to cut through all the fluff, you are absolutely in the right place. In this explainer, we're zeroing in on Chapter 4, Atoms, Elements, and Ions. We're going to lock down the core concepts you actually need to know to ace this test. No distractions, just high-yield facts and clear visuals to get your brain completely exam ready. So let's just dive right into it.
Here's our game plan. We're breaking this down into 4 quick sections: atomic structure, the periodic table, ion formation, and finally, isotope calculations. We'll build logically from the absolute smallest subatomic particles all the way up to doing some exact isotope math.
All right, kicking things off with Section 1, Atomic Structure and Particles. This is our foundation.
Now, before you can predict how any chemical behaves, you really have to understand the fundamental building blocks of matter. Every single sensation you experience comes down to these incredibly tiny particles, and to understand them, you've got to internalize this foundational quote: "Atoms are mostly empty space." Back in 1909, Ernest Rutherford fired alpha particles at a super thin sheet of gold foil. He expected them to just pass right through, but a few deflected at these crazy sharp angles. This completely proved that an atom's mass isn't just spread out evenly, it's concentrated in a remarkably dense, positively charged nucleus. Just to give you an idea of how mind-bogglingly dense this is, if solid matter were made entirely of these nuclei, without all that empty space, it would literally be as dense as a neutron star. Crazy, right?
To really wrap your head around the scale inside that atom, think about this comparison. We've got 3 main subatomic particles: protons, neutrons, and electrons. Protons and neutrons, they hang out in that dense nucleus and have very similar masses. But the electrons, they have almost negligible mass. If a proton were the size and mass of a baseball, an electron would be nothing more than a single grain of rice. Seriously, visualizing that will absolutely save you on those tricky multiple-choice questions about atomic mass distribution. I'd actually highly recommend you screenshot this table or just lock it into your memory right now. It is your ultimate cheat sheet for homework and the exam. It breaks down protons, neutrons, and electrons by both mass and charge. And hey, here's the golden rule of electrical charge you have to remember: opposite charges attract, while like charges repel. In a neutral atom, your positive protons are perfectly balancing out your negative electrons.
Okay, moving right along to Section 2, Decoding the Periodic Table, the ultimate map. Now, I really don't want you to look at the periodic table as just some random list of elements you have to painstakingly memorize. Instead, think of it as your ultimate map. It's a perfectly organized tool built entirely on predictable, recurring patterns. First things first, the entire table is organized by the atomic number, which is represented by the letter Z. The atomic number is simply the number of protons in the nucleus. And this number? It is the absolute identity of the atom. If you change the protons, you literally change the element entirely. Oh, and a fun fact to keep things interesting: a lot of these element names actually tell a story. For instance, bromine takes its name from the Greek word for stench because of its incredibly strong-smelling vapor. So next time you see Br on the table, just think stinky.
So the crucial point here is knowing the geography of this map. We can broadly divide the table into 3 categories. Over on the left, we have metals. They're shiny, good conductors, and critically, they tend to lose electrons. On the upper right, we have nonmetals. They're poor conductors and usually gain electrons. And sitting right there on the border between them are the metalloids, or semimetals. These act as semiconductors, which is exactly why they're absolutely essential for modern computer electronics. You also need to know your key vertical columns, or groups. Main group elements follow highly predictable patterns, unlike the transition elements sitting in the middle. You've got Group 1A, the highly reactive alkali metals. Right next door in 2A are the alkaline earth metals. Way over on the right in 7A are your highly reactive nonmetals, the halogens. And finally, Group 8A, the noble gases. These guys are famous for being chemically inert, meaning they rarely react with anything. They just kind of do their own thing.
Which brings us to Section 3, Forming Ions and Charges. I like to call these the chameleons.
Matter is normally charge neutral, but when that balance gets disturbed, think of the dramatic, rapid rebalancing of charge during an electrical storm that creates lightning. Atoms gain or lose electrons. When they do, they become charged particles called ions. So how do we predict what charge an ion will take? Just follow this easy 3-step procedure on test day. Step 1. Identify the number of valence electrons just by looking at the main group column number. Step 2. Decide if it's easier for the atom to gain or lose electrons to match the electron count of its nearest noble gas neighbor. Step 3. Write the charge with the magnitude first, followed by the sign.
And this brilliantly illustrates the 2 types of ions you're going to form. First up, cations. These are positive. For example, a lithium atom loses one negative electron, which leaves it with more positive protons, so it becomes a positively charged lithium ion, Li+. On the flip side, we have anions. These are negative. A fluorine atom gains one negative electron, so it tips the balance to become a negatively charged fluoride ion, F-. Remember, gaining an electron means gaining a negative charge. It sounds a little backwards, but keep it straight and you'll be golden.
All right, home stretch. Let's move to our final section, Section 4, Isotopes and Neutron Calculations. We've established that the number of protons is set in stone, right? It defines the element. But what about those neutrons hanging out in the nucleus? Well, their numbers can actually vary in nature. These natural variations are called isotopes. By definition, isotopes are variants of the exact same element, meaning they have the exact same number of protons, but they differ solely in their neutron count. Every single element has a unique natural abundance of these variations. They're still the same foundational element, just slightly heavier or lighter versions.
You will absolutely be tested on how to read isotope notation. There are two standard ways you'll see this. The first is with the chemical symbol, where the mass number is a superscript on top and the atomic number is a subscript on the bottom. The second way is much simpler. It's just the element name, a hyphen, and the mass number. For example, neon 20. Don't let the different formats throw you off during the test. They're giving you the exact same information.
And here is the golden mathematical formula for your exam. To find the number of neutrons, take the mass number, which is your protons plus neutrons, and simply subtract the atomic number, which is just your protons. Mass number minus atomic number equals neutrons. It is truly that straightforward.
Let's actually prove how simple this math is by looking at the three naturally occurring isotopes of neon. Neon's atomic number is always 10. That never changes. So for neon 20, 20 minus 10 leaves us with 10 neutrons. For neon 21, 21 minus 10 equals 11 neutrons. And for neon 22, 22 minus 10 gives us exactly 12 neutrons. Just plug those numbers into the golden formula and you are going to get the right answer every single time.
So we've seen how the periodic table flawlessly acts as a map to predict these exact chemical behaviors, from ion charges all the way to mass variations. But it really begs a fascinating question. If Dmitry Mendeleev could build this table just based on observed patterns over a century ago, what deeper, hidden theoretical laws actually forced these atomic patterns to occur in the first place? Well, hold on to that curiosity, because that is exactly the profound mystery we're going to unlock when we tackle Chapter 9. Until then, use these rules, trust the patterns we covered today, and go crush that Chapter 4 exam. You've got this.